All right, guys, welcome to our final lecture on gas laws. This is the ideal gas law. So let's first just give you that formula and make sure that you know what the variables represent. PV is equal to nRT, okay? Now, a quick scan of this gas law and you will notice that there is no P1, P2, or V1, V2, or any other variable with the subscript, and that is because this gas law does not examine changing gases. Okay, we'll talk more about that in a second, but first let's write down what these variables represent. P is equal to, of course, pressure. Now, in the ideal gas law, using the constant that we're going to use, pressure must be in units of atmospheres. Now, if pressure was not in units of atmospheres, you would have to convert it into atmospheres to do this problem correctly. Are you going to have to do that? No, you won't have to do that right now, but as we go on with chemistry, I might give you the pressure in kilopascals, and then you'd have to convert it to atmospheres before you could use it. For now, the pressure is always going to be in atmospheres, so it's going to be easy for you to just practice doing the math calculation. So P is pressure. Of course, V is volume, and in this law, volume must be in liters, okay? Now we have something new, all right? We have lowercase n. N represents the moles of molecules of the gas. So this is the moles of the gas. Don't confuse that with volume. Volume is the space that the gas occupies. Moles are the actual numbers of gas molecules, okay? All right, now we've got something else new, R. R is known as the universal gas constant. Now, this is a given value, like pi. You know, when you're solving problems with circles, you can use pi, 3.14. Well, we have that for gases too, and it's called the universal gas constant, and it is the following value, 0.0821. Here's the units, liter atmospheres per Kelvin mole. Now, I want you to be careful with this unit, okay? I want you to examine it carefully here. Specifically, I want you to look at the units that are right there, okay, that I've highlighted. Those units you will see are all of the units that are required for values in the ideal gas law. For example, liters. Well, look up to V for volume, it's in liters. Atmosphere, look up to P for pressure, it's atmosphere. Kelvin, well, we haven't talked about temperature yet, so let's do it. So temperature is T, and temperature must be in Kelvin, okay? So you got to convert it. And you could see it in the universal gas constant. And then moles, the numbers, right? You see that? So why do we have this universal gas constant? Let me give you the easy, simple answer. Without the universal gas constant, we would not have the cancellation of units as we do the mathematics. And we would not have a unit that we could use to represent anything logical for us. So we have this universal gas constant. The value is 0.0821, and that comes from calculating gases and their behavior at what is known as standard temperature and pressure. We're not going to get into that right now, but that's where that number comes from. Okay, so basically, to keep it simple, that number allows us, it is what is called a proportionality constant, and it allows us to cancel out units to get the one that we need for solving the problem. Okay, but basically, it's a free value for you to plug in. Okay, so there we have the ideal gas formula, and I'm going to put it in a puffy cloud because you're going to be using it today and for your homework, okay? Now, what the heck is an ideal gas? All right, it's called the ideal gas law. It's like you should only apply it to ideal gases, right? Well, if you remember back to what we talked about with the kinetic molecular theory, we were talking about gases behaving according to this ideal gas law idea, all right? And so what it is this. This gas law applies to all gases that obey the kinetic molecular theory. So for number one, things that you might remember about the kinetic molecular theory is that a gas's temperature is equal to the average kinetic energy of the molecules that are in it, okay? Remember that in a gas, all collisions are elastic. You remember that? Okay. And remember, we say that gas molecules are so far apart, they don't interact. They don't affect each other. Now, there are a few other points here, but these are kind of the main ones that we talked about. So, an ideal gas, remember, is describing all of the gases that you would encounter in your daily life here on Earth, unless you went to the center of the Earth and had a gas sample where there's enormous pressure, or you went into outer space where the temperature is so low that maybe gases don't behave according to the ideal gas law, or don't behave as ideal gases. But for all intensive purposes, you can just know that gases in your experience will follow this ideal gas law. Now, that was a long explanation of why you can use the ideal gas law. And using it is the next step. So let's get into it, all right? Why would we use it? Well, we would use the ideal gas law if we knew some things about a gas and we were missing a piece of information, okay? So, for example, let's just say that we knew what the pressure was, we knew the number of moles, and we knew the temperature, but we didn't know the volume of a gas. And I said, hey, I need to know what the volume of this gas is, okay? So if you knew the pressure, and you knew the number of moles, and you knew the temperature, you could solve for V, all right? Now, one thing about the ideal gas law is when you solve problems with it, it's easier to change the equation around with the letters before you plug in the numbers. Let me show you what I mean. If we were solving for V, I would want to have a formula that says something like V equals and then something in here, right? If I had that, then my life would be easy, right? Then I'd be happy, okay? Well, what can I do to move the variables around in the ideal gas law to make my life easy? Here's how we do it. If I'm solving for V, can't I divide this side by P? And if I divide that side by P, I have to divide this side by P. These two cancel out, leaving me V equals nRT divided by P. So that's the same thing as right up here, nRT divided by P. So my suggestion to you, and I'm going to put this here in the notes, is that solve for the variable before you plug in values. Okay? This is a good idea because it just makes the whole solving process neater and cleaner and easier. Okay? All right. So knowing that, let's go ahead and look at a problem and solve one. All right? Let's do that. Okay, so your first practice problem. A scientist has a 2-mole sample. All right, let's just start highlighting what we know. So you have a 2-mole sample of the gas at a temperature of 5 Celsius and a volume of 10 liters. And so what is the pressure? Okay, Let's solve this. So the first thing I would do is write down what I know. So moles, N is equal to 2.00 mole, right? Boom, there you go. Remember that N, that's a new value for us, right? That's a new piece of information that you guys haven't studied before. So just be aware, go back in the notes and you'll find it, okay? The gas is at a temperature, so temperature is equal to 5.00 Celsius. Now instantly convert that to Kelvin. Okay, 273 plus 5 is 278 Kelvin. All right. And then you have volume is equal to 10.0 liters. All right. And P is the unknown, right? You're solving what is pressure. We're missing R. Remember, R is free, so always write it down. 0.0821 liter atmosphere per Kelvin mole. Now, guys, I know you've all been listening, but there will be a student now who is not paying attention, who's playing Call of Duty on their dumb computer, and they're going to look over and they're going to go, where did you get R from? Well, R, remember, is a free value that's given to you. It is a constant, so you're always allowed to use it, okay? All right, so let's write down the formula. PV is equal to nRT. We're solving for P, all right? So let's manipulate this equation to get the formula that we want, all right? So we divide by P, we divide by P. That gets rid of that, leaving us V is equal to nRT divided by P, okay? That was a nice little trick we did there. And now I want you to look at something else. I've got liters here, okay? I've got liters here. Well, that's going to cancel out. I've got atmospheres here. I've got, nope. So atmospheres will be our final unit, okay? You can see that, right? There's nothing to cancel out atmospheres. So it will be our final unit. What about Kelvin? Yep, there's Kelvin. That's gone. And what about moles? Moles, yep, that's gone. So if we know that the final unit is just going to be atmospheres, let's just use the numbers without the units, okay? So here we go. V is going to be equal to 2.00, that's the number of moles, times 0.0821, the gas law constant, times the temperature, which is 278, right? And what's going to be on the bottom? Pressure, and pressure is 10.00. All right, do the math. When you finish it, when you do that math, okay, and you solve all the way out here, wait a minute, Mr. Ashley. You guys didn't tell me. Look what I did. We're not solving for V. We're solving for P, right? The good thing about this is, since these are next to each other, they're interchangeable, right? So actually, the formula, let's rewrite it. Let's make it neat. See this, guys? Sometimes you make mistakes, right? Let's rewrite it. We're going to solve for P. So let's do this. PV is equal to nRT. If we're solving for P, we divide by V. Now we're on the right track. And therefore, P, oh goodness, is equal to nRTV. Okay. Yeah, you know, mistakes can happen. Make sure you're paying attention. Good thing I was. So P then, let's plug in the values again. All the values are going to be basically the same, right? So it's going to be 2.00 times 0.0821 times the temperature, which is 278 Kelvin, divided by, that's right, divided by the volume, which is 10.0. All right, now, whew, good thing I checked that. Pressure, when you do that, okay, you want to multiply the top first. So you're going to get an answer, write it down, 45.6476, and then divide it by 10.0. Do these steps separate, right? Multiplication, then division, and your pressure will end up being 4.56 atmospheres. And how did I know that the unit was atmospheres? Well, if you go back up here, the only unit that's allowed that it has not canceled is atmospheres. And so there is your final answer. Nope, don't do that. Let's do this. All right. Okay, woo, man, let's move on. You got to be careful with these things. Take your time, double check your answers. Let's do another one, okay? Practice problems. How many moles? Ooh, I see something. You're solving for moles. If you're solving for moles and you know it, just write it down. N is equal to unknown, okay? Of CO2 are contained in 15 liters. So volume is equal to 15.0 liters. Temperature is coming up, right? It's at 100. So temperature is 100 plus 273. It's going to equal 373 Kelvin. Now we're on the right track. The pressure is, ooh, that's a high pressure, 17.5 atmospheres of pressure. And atmospheres is the unit we want. Remember, R is free. 0.0821 liter atmospheres per Kelvin mole. Now let's see if everything cancels, right? Liters with liters, atmospheres with atmospheres, Kelvin with Kelvin. Ooh, the only thing left is mole, and that's what you want up here, right? That's what you're solving for. All right, so now let's rearrange this equation, right? PV is equal to nRT. And so you're solving for moles, right? So it's going to look like this. Divide by RT, divide by RT. So N is equal to PV divided by RT. If you do that, you will have N. So let's do it. Okay, let's plug in what we know. So we know pressure is 17.5. And I'm not going to use the units because we know they cancel out correctly. Volume is 15.0 liters. Okay, R, of course, is 0.0821. And T, temperature, is, okay, 100 plus 273 is 373, right, guys? Am I doing that right? Yeah, 373. All right, and that should be equal to N. So get out your calculators. I've got mine out. And let's do the math together, okay? So when we multiply the top, we know that we get 262.5. Now let's multiply the bottom, okay? So get your fingers tapping, 0.0821 times 373 equals, and I get 30.30, and write it all the way out, 30.6233. Now get ready for some division, right, guys? Here comes some division. So 262.5 divided by 30.6233 equals, and I get this number, 8.5719 is equal to N, but we need 3 sig figs. 1, 2, 3. Is that a 5 or larger? No. So the answer is 8.57 moles equal N. Ooh, there it is, guys. There it is. We've solved it. It's looking good. We got a final answer, and we even caught mistakes that we made as we went through this problem, okay? So that is how you solve problems using the ideal gas law, okay? This video, I'm going to be posting it up later tonight on my YouTube channel. Refer back to it if you need help.